All right, welcome everyone to part 2 of our series, FEA modeling from start to finish. In part 1, we cover pre-processing of a structural bracket, and in part 2, Ryan Tadman is going to take us through the post-processing and analysis. So Ryan Tadman, he joined SDA as a full-time stress analyst in 2015. He has worked on projects such as UAV and the forward bay and launch abort system for the Orion crew module. And I'll let Ryan go ahead and start up.
All right, so today we're going to do FEA modeling from start to finish, but this is part 2, so we'll just be doing post-processing. So first we're going to run through the static analysis. I'm going to give you a quick overview of what we did last time as far as setting that up, and then we're actually going to run it. We're going to go into enveloping the results. We're going to visualize some of these results in FEMAP. I'm going to show you some good tools to kind of manipulate and get good plots and extract data. We're going to explore some of the data conversion options that FEMAP has. And then we're going to go through kind of like a mock situation where you want to identify failure regions and kind of look farther into those. We're going to create a custom result vector. Those can come in handy for writing margins or visualizing margins. And then we're going to identify some artificial stress risers and remove them from the data set. And then we'll go into some CBush visualization and data export. So we're just going to switch over to FEMAP right now and get started. All right, so for those of you that were here during part 1, this should look familiar. It's essentially a pressure vessel, or at least a section of it, and then we've got this set of brackets and some supported mass. So last time we meshed it up, we have a mass element to represent the mass, but most of it's all these plate elements that we made last time. It's all been hooked up, and then we made a linear static analysis set. So I won't go through all this again. You can check out our part 1 on YouTube or on our website if you're interested in any of how this was done. But we've got 16 subcases with different accelerations in one single static analysis. So how you're going to do this is through here you can just click on here and click Analyze, or simply you can just right-click under the analyses and Analyze. So it's going to pop out your analysis window here, and it's going to give you some useful data. So it's going to tell you how it's doing, what it's doing. This is going to be a really short one, so we probably don't care about anything it's saying, so we can pin that over here, and we can get to it whenever we want. So it's going to run and tell us what it's doing down here. It shouldn't be too long. All right, well, I guess it's decided to take its time. So just to go into what it's doing is it's running the analysis. Sorry, this is some leftover stuff. Then it's going to output all of the results to an OP2 file, which is just a standard output file over in the root directory of your FEM model. All right, something isn't happening quite right here. Is it? Oh, never mind. It's just taking a long time on the laptop. All Yeah, sorry about that. So this is going to input an analysis study. So it's an analysis set that has all of the 16 cases we ran. So in this case, they output with case 1, 2, 3, 4, all the way through. And we can always go back to our loads and figure out what order they were run and pull them in. But sometimes it's useful to have actual pertinent information in the titles here. So that can be changed by going to File, Preferences, and then we can go to Results, the Results tab, and under Output Set Titles, we've got a few options. So the title is going to be the title of the analysis. So in this case, it would be static. You can see over here. We want subtitle. So that's going to be the title of the subcase. Click that, and we can, I'm actually not going to delete this just in case this takes some time. This laptop must be a little slower than the desktop I was doing this on. Now it's going to be quick. Okay, so while that's importing, we'll go over some of the stuff we're going to do next. So we have all these individual cases, and we could just open each one by itself, look at the results, decide what we want from it, write it down, and write margins based on that. But a lot of times it's useful to envelope them. So it's going to go through each of these cases and pick it's going to pick the largest value for each output vector and put it into its own analysis. So what we're going to do here is we'll select all of these, right-click, and we can click Envelope. We've got a few options. So we can pick max value, min value, or max absolute value. Usually you're probably going to want a max absolute value because that's going to pull in your driving cases for compression because that's going to be negative number, and you want the largest negative number. So all that's doing is calculating, and it's going to make a new set. So it's going to be 33 and 34 over here. And we can use that to run the analysis. All right, so how we can do this is just double-click on our vector, and that's going to activate it, or not vector, but set. And now we can see, by clicking this button up here, the contour view, we've got some stresses. So we can go over to our Post tab and click the contour here, and that's going to give us a lot of options. So here you have your output set, and that's what we just made on the other page, right? So we've got all of the ones here. These are duplicate just because I haven't deleted the other ones, but we can activate this. It's already activated. And then we pick an output vector. So that's the information that it's giving us. And we've got a lot of options. You can do, translations, rotations. Here we've got our C-bush forces. If you were here last time, you know that that was to represent bolts. We've got plate top stresses, bottom stresses, and then all of these individual laminate ply results. So let's just pick plate top von Mises. It's a pretty common one to be interested in. And you can see here that we've got all this data coming in on the contours for this, but not on these clips. And that's because these are laminates, so it doesn't have a top von Mises stress. So you can activate those by going to additional vectors, and it'll give you two more options that you can use. So these are just the same things, and we're just going to pick laminate ply 1 von Mises, just something to compare it to, and we'll see that it pops up here. So how this works is if I were to pick something that was overriding the original one, so if I went to plate top major principle, might be interested in that, it's not going to change anything. And it's because if you're telling the same element to display two vectors, it's going to pick the first one that's listed and not show the second one. So let me just throw this back to our von Mises. All right. So you can see over to the right we've got our contour legend, and it's telling us stresses in PSI. And it's just PSI because that's our units that we've used. So you can see our peak level is 22 KSI, and it's probably somewhere over here or over here. So there's different options you can do for data conversion. That's essentially what FEMAP is doing to show this contour. So I've got no element averaging on right now, but there's also average, max, min, and then all of the same options with the Centroid only results. So how these work is no element averaging, essentially. If you zoom in here, you can look at it. each element has corner results from Nastran. So what this specific one is doing is it's displaying the corner results as is. So you've got this element that says this corner is a certain stress, and this element says the corner is a different stress. So you can see there's kind of a discontinuity there. So the average does just that. If you're interested in this node, it's looking at what this element thinks it is and what this element thinks it is and averaging them. And it does that everywhere, so you get a smoother contour. And then maximum and minimum do just that. It's this node has information from both, and it's just going to take the maximum. The minimum will take the minimum. The Centroid only, as all similar logic, it just only uses Centroid data. So this element has a certain centroidal value that it pulls out from Nastran, and it's only going to use that. And if we put the average on, then this node will be equal to the average of the 4 centroidal data that it's looking at. So we're just going to stick with no average centroid only as a simple option. So now we want to identify failure regions, because that's the whole point of doing an analysis. So we probably want to break this into individual parts that we're doing. So if, let's say, we're interested right now in this plate alone. So one way we can do that is just to go over here to our Draw Erase toolbar. We can select Properties, and we'll just pick this metallic property and click OK. So that's going to hide everything except for this property. So now we're only looking at our metallic bracket. But you can see over here that the stresses didn't change, and it doesn't look like there's a 21 KSI stress on here. And that's because the contour is set by the entire model, not just this. So we can fix that by going over here, and we can create a group. So we can just call this metallic bracket. And that's going to create a group over here with everything that's being shown right now. So if we show active group, it's going to disappear. Okay, so let's see what happened. Okay, we'll try that again. All right. Grab this, and there are a few bugs with this. I've noticed that if you do grab a property and try to add it, it does have some issues. But I know one way to work around it is, and a good way to show this thing is you can grow your group. So this is just selecting all of the elements in your group and then grabbing the next element that's contacting them. So this grabbed in all of our RBEs. And we can continue to grow it if we wanted to, pull in more, or shrink it if we needed to. Now we should be able to create a group. And this should work. Okay, so now we've got our group, and you can see our contour over here is adjusted. So we've selected our group, and now our contour says, well, the largest stress in this group is 16 KSI. And we'll see it's over here. So there's a few things we can do with this, with our post-processing. We can define our levels. So all that red means in this case is that it's the largest in this group, which really is not relevant when we're looking at failure. So what we can do is just set a value that we want to say that this fails at. So we can say that at 10 KSI, this metallic bracket is going to fail. So how we can show that is go under level mode, under the levels tab you've got here. You can switch over to max min, and you can set a maximum value. So we'll just do 10,000 PSI or 10 KSI. And now that's going to override and make the maximum 10,000. So now everything that's red is near 10,000. But that also has another problem, because the stuff that's just under 10,000 is going to look as red as the stuff that's just over 10,000, because you're not going to be able to pick that up. So one easy way to get around that is to go to your criteria view. So the criteria view, sorry, I'll turn off those labels. So this is showing the same data, but it's locked at Centroid only, no averaging. That's the only thing that this will look at. So it's limited in that respect, but it does give you a lot more options that you can set limits. So if you want to set your limit to anything above 10,000, you can set that and then say you don't want to look at elements that don't pass your criteria, right? And now you only see that. But that's not very useful because it's kind of hard to get context. So what you can do is just turn the labels off, and you'll see that it sets them at a certain view color, and you can change the view color through here if you don't like the blue. So now we can see these are all of the elements that pass our criteria. So we said that anything above 10 KSI passes our criteria, and I want to show them. So in this context, it's showing the elements that fail. So another thing you might want to do is a lot of times when you're modeling bolts with RBEs, you don't want to take into account these stresses. And that's due to the stiffness differences between an RBE and an actual plate element. These are a lot of times considered artificial, and you'll solve for these stresses with hand calcs when you're actually sizing things. So in that case, you don't want to show the results in your plots. So what you can do is use a group. So here we're going to use our same group again, and we'll just create it in the same way just to show you how that works. So we've selected our property, and now we're seeing the property, but we want to shrink it. So we don't want to have those first two nodes. So we can shrink, and we'll just shrink one time. So now we've taken out 2 rows around those RBEs. And we should be able to create a group from this. And we'll call it the analysis group. So we should be able to go over, activate our analysis group, and now we're only showing our analysis group. So this is an easy way to kind of view what you care about. So these might still be stress risers, but that would have to be something that you picked on your own, or if you decided to take out more than 2 rows, it's your discretion. A lot of times you don't want to send a picture that looks like this because you'll get questions of what the square holes are. So a way you can do this is to bring your metallic bracket group back to visualize. So you're showing the whole thing, but you don't want to show results on those first 2. So you can go to your Post-Processing tab, and under Show on Groups, you can just select Analysis Group. So now it's going to show the results on everything you have in your analysis group and just leave the same property colors on everything that's not. So a lot of times you'll see people just go through the Modify Color property and change this to something unassuming, like a light gray. So now you can explain that these elements are here and they represent circles where these bolts go through, but we're not taking the Nastran stress from them. All right, so sometimes you don't want to show a graph that just has 10,000 PSI on it. You want to show a margin. So FEMAP does give you the option here to create your own vectors. Remember, the vectors were just the elemental and nodal results. So how you can do that is go to Model, Output, Calculate. So you're going to open a window, and this is asking you where do you want to put this vector, right? Because we have output sets and output vectors. So we'll just put it in the envelope because that's an easy place to find it. So we've got a creative title for it, and we'll just call it Margin of Safety, or MOS. We're interested in elemental data, right? We want to know if this element fails. And now we have to write an equation. This is kind of beyond the scope of this webinar, but I'll explain to you where you can find the syntax of it. But what we want to do, and I'll walk through this one specifically, is we want to define 10,000 PSI as our failure. And then we're going to divide that by the vector, right? And the vector we want is in the envelope group, which you can see over here is output set 33. We want output vector 7,033, right? That's the plate top von Mises. And then we define our variable. So this is just unique to FEMAP, but we just need to type exclamation I. And then we subtract by 1 because it's a margin. So we click OK, and it's going to ask us to select elements. We care about our analysis group, so we go under group, we clicked analysis group, and then we clicked more. And we're just going to make sure that's what we want. So that's what we're going to calculate the margins for. We click OK. So what that did is it put on the bottom and it's just standard 90 million. It will add up. If you calculated another one, it would be 90,000,001. So now we're showing that. But remember, we set our max and min to 10,000, and there's no location on here that has 10,000. So what we want is to set our max to something like 1, and we'll just set our min to -1. This is also kind of confusing because, something might be a little green. So a lot of times you want a Boolean. So we'll drop this to 2. This is just the number of colors. So now we've got 2 colors. And we really don't want a gradient because we want to just know if it fails or passes. So we're going to take continuous colors off. So now we've got this magenta color that shows it's failing and a red that shows it's passing, which is usually the opposite of what you want. So we can go to the contour palette and just click this color contour over here. And there's a standard here, and you can change it and do whatever you want. If you don't want magenta, you can take those out, and then we can reverse them, which is the important part. So now everything that passes is going to be this dark blue, and everything that fails is going to be this red. So now we can see that with our criteria, we've got 2 things over here that might be a problem, and then 1 here that might be a stress riser or could be a problem. So that's an easy way. It's a couple tools you can just go in and kind of decide, show good graphs on what's failing, and it's an easy way to pass information to people that might not be have a stressed background. So I have a couple notes on here just about this section to help you just kind of get a feel for everything. So I'm just going to set everything back to kind of the standards so we can talk about some of the other options that you have in here. And we'll just set this to a standard average one. Okay, so a couple tools you have here is with the entity info box over here in the bottom left. This will pull out anything that it knows based on the vectors. So you can go to list model element, and if you just go over in the corner, remember this is where we found some problems. We can just hover over this, and you'll see in the bottom left corner, it's going to give us not only the element number, but the property, the material, and then that where it says top ply, plate top von Mises stress, that's going to be the Centroid data, and it's going to give you all 4 nodes based on this element. And you'll see this element is different. So that's a good way to pull out specific data if you're interested in it. Another thing you might notice is that there is somewhat of a difference between this. When I pick automatic, you can see my peak is 15. If I pick, oops, sorry, that's the wrong field. Yeah, average, you see it's 15. No element averaging, you'll see it's 16. We go to maximum, and we'll get about 16. So the difference in those values kind of tells you how much fidelity you have, right? So if those are really close, it means that you have an accurate model of how that is. It's saying that all options agree. Whereas if those are really far apart, you might need to think about increasing the fidelity of your model because you're going to have some inconsistencies, and you haven't really converged on the correct result. Another thing is that in your up here in your criteria view, you can turn on those labels that I turned off initially. So that's going to tell you the results for each element. So in this case, it's telling you the centroidal results for the plate top von Mises stress. And another powerful thing about this envelope is when you're looking into it and you found what your failure things are, you might know want to know what causes it. But when you created the envelope, you also get an envelope set info. And what that is what load cases drove that largest value. So here you've got 22. So if you go over to your results, 22, now I know that it was this combination that created that maximum load. All right, so we're going to go back to this, and this looks odd because we still are in that set info. So I'm going to quickly go over what we can do for C-bushes, and those are used for bolt analysis. So I'm going to go back to showing the full model. We've got our C-bushes in there, and you'll see if I just choose my contour view and I go over here and I select, we'll say bush X force, it's going to color the C-bushes based on their loading, but that's not a very good way. So I'm going to turn off my additional vectors here because I was having my contour being driven by my von Mises stress in the laminate ply 1. So that's not a good way to do it. I can go to my criteria view, and I'll turn off my limit, and I'll turn on my labels. And it's going to tell me on each one what it is, but that's still not the best. So there is a contour arrow view, and what that's going to do is draw your arrows on each one for each one. So it's easier to see if you put in wireframe up here. So now you can see, and we'll just turn off this scale by magnitude because it makes it a little hard to see. So now you can see we have our 3 direction forces for that C-bush. But if it's a bolt, we're more interested in shear and tension. So what we can do here is through this level mode in your levels drop down, it's set at automatic, but that's not the right one. Sorry about that. Arrow display mode, we've got automatic. I know because we just made this model that the axial is in the Z defined. So I would click this, and you can check that by going to modify, sorry. Yeah, modify edit property. And if we click that C-bush, you'll see we've got our free dimension in the 6, which is Z. So we've set that as axial, so that's right. And it automatically resolves your shear and tension for you. So we know that on this bolt, there's 350 pounds of shear and 31 pounds of tension. So that makes it easy to see where these bolts are and how much loading is on them. But that's not always the best option when you have hundreds of bolts and you need bulk data. You're not going to go to every single one and write them down. So this is where the data table can be helpful. So first we need to unlock the data table, and we can use the list output results to data table. And this is going to give us some options. So output sets we can list in rows or columns. We're only going to ask for one output set, right? We only need the envelope set. So this one doesn't matter in this case. Our output vector we can have in rows or columns. We'll have them in columns. And our nodes and elements we'll have in rows. These are elemental data because it's a C-bush. But if you do have nodal data, it is important to define or at least know what coordinate system you're in. So I'll click OK, and this is going to ask me what output set I want. So I want my envelope, and it's going to ask me what output vectors I want. So I'll just say X, Y, and Z. So you click OK, and it's going to ask you to pick the elements. So just to make it quick, I'm going to go under the method type, and then under type, I'm just going to pick spring damper. That's a C-bush. Click more, and you'll see it selected all the C-bushes in my model. Then we'll just click OK. So what that did is it populated the data table with all that C-bush forces. So this is a pretty simple spreadsheet. You can sort, you can filter up here, but you can also copy. This copies it to the clipboard, and it pastes very cleanly into Excel, where you can find your RSS shear and do all of your sizing and margin checks. So that's all I have. I'm just going to run through and give us an overview of what we did. So we enveloped the results, and then we learned a few things on how to visualize them in FEMAP. We learned about the data conversion. We identified some failure regions. We created a custom output vector, which I'm going to show you right now how to find more information. And actually a lot of good information can be found in this location. So if you go under Help and Help Topics, this is going to give you a database of basically everything FEMAP. So there's a bunch of options in here that you can go through on your own. But under post-processing, Sorry, I can't seem to find what I was looking for. I'll search for it. So we want data, or no, we don't. All right. Sorry about this. I will find it, and I'll get back to you after we have a word from Aswin about SDA.
Great. All right. So please type up any questions that you have in the questions pane on the right side, and I'm just going to show a few things. Just have a few slides to cover. So, there we go. First, I just want to, next Tuesday on January 17th, we're hosting a symposium at Piper Aircraft in Vero Beach, Florida. At the symposium, you'll get a chance to see the case study of how our team and Piper used FEA to create the new Piper M600 wing, tail, and fuselage. And this free event includes a tour of Piper Aircraft, food, and a chance to speak with Mark Sherman and Andy Haynes from the FEMA development team. So that's a great opportunity to discuss about any things that you'd like to see in the program or any problems that you're having. The FEMA development team does a great job of addressing those concerns. And you can find out more information at structures.aero/FEMAP symposium, and you can go in the chat and see that link. And then just a brief introduction into who we are. We are Structural Design Analysis, also known as Structures.aero. We're a group of 14 aerospace stress engineers that provide structural analysis for companies such as Lockheed Martin, NASA, and Vanilla Aircraft. Some projects that we have worked on include the NASA Orion Composite Crew Module and the Vanilla Aircraft V1 UAV that just achieved a world record for nonstop, unrefueled flight at 56 hours. So really great projects that we get to work on, and our engineers use software from Siemens PLM and Collier Research Corporation, including Hypersizer, FiberSim, Solid Edge, SimCenter, and of course FEMAP with NX Nastran. And we'd like to, we've shown the complete process of modeling a bracket, but the best way to learn would be to try for yourself. So you can try FEMAP with NX Nastran for 45 days using a free trial that doesn't require credit card information. And as a bonus that only SDA provides, we have created a tutorial that takes you through the steps to model a mechanical arm, and the geometry file for that tutorial is provided so that you can follow along using the free trial. And you can visit structures.aero/download FEMAP to get more information about that. And lastly, if you have further questions, you can contact Ryan Tapman, and his information is provided here. And if you have questions about pricing or want to see a demo or would like to learn more about the product configurations that we have, you can contact our Director of Sales, Marty Civic, at mcivic@structures.aero. So Ryan, I'll pass it back to you.
Okay, so I found it. Sorry about that. I have it up on my other computer. I just wasn't prepared. So under this help topic, you can go to post-processing, and under analysis studies output sets, there is something called, well, this is all of the options you have here, but model output calculate. That will explain what each of these boxes are, and then if you follow this link, it will explain how to write the equations. So I'm going to go into some of the questions I got. Most of them were fairly simple. I have one saying, in the case of mating parts, can we analyze contact stresses? And yes, you can. So contact stress is an output vector, and that will come in through here, and it'll just be an option. I don't have the time to run a contact analysis right now, obviously, but it will just be a vector in here that will say contact stress, and it'll pop up just like any other vector. I do have a comment that I left out factor of safety. That is true. I guess I was assuming that the 10 KSI would have been after the factor of safety. I have another question saying, can it output the shear and axial as it was plotted? I have heard rumors that it can, but I didn't quite have time to figure out how that works in this case. So I can look into that and get back to you with that. But if there aren't any other questions, I think that will that'll wrap us up. All right, thanks everyone for coming.